SwayamPrabha. Digital India. Educated India.
Hello, welcome to lecture 24, where we will be continuing our discussion on shear center of open thin wall cross section beam. So, in the last lecture we have defined shear center shear center as the point, let me abbreviate it as SC. So, we have defined that shear center is that point on the cross section, on the plane of cross section of the beam through which the shear forces should pass, so that the torsional moment produced because of the shear forces are equal to P0. So, if we have any arbitrary shaped thin wall cross section, so let this be the cross section of the beam. This is thin walled open. So, for closed cross section beam we have to discuss it in a different way. So, thin walled open cross section of a beam. So, let this be the x and y axis. Now, shear center is that point on the plane of the cross section of the beam. So, this is the shear center, such that if the shear forces passes through this shear center, the shear forces, that is Sx and Sy, if they passes through the shear center, then there would be no twisting or torsional moment in the cross section. So, if we write it down, shear center is the point So, this is the definition of shear center of a cross section. So, it not only holds for open cross section beam, this definition holds for closed cross section beam as well. But let us right now discuss about open cross section beam, and then we will move into a closed cross section beam. So, this beam has an say a thin thickness, an uniform thickness, T, which is small. So, this is a thin wall cross section. Now, there are certain other properties of shear center, which let me state it right now, and we will discuss this in detail as we move through the lecture. Properties of the shear center. Now, the first property is that if a cross section has an axis, has one or two axes of the symmetry, then the shear center must lie on that axis of the symmetry. So, for a cross section with one or two axes of symmetry, the shear center lies on the axis of symmetry. So, this is one property of shear center. The next property is that any shear load that does not passes through the shear center can be represented So, let me now discuss this. So, what suppose I have a set of shear forces which are not passing through the shear center, but passing through another point which is not the shear center. So, I have S x and S y, or let me write it with the red color itself. So, I have S x and S y which is passing through the point which is not. So, it is passing through a point P where P is not the shear center. So, in that case, how are we going to analyze the problem? We are going to shift this force here. So, we are going to just move this S x and S y here, and we will find out the torsional moment mt of this force S x and S y about the shear center. So, this is how whenever I have a beam where the shear forces do not pass through the shear center, then we have to consider an equivalent system where we move the shear forces to the shear center. Additionally, we consider a torsional moment mt, which is obtained by taking the moment of S x and S y about the shear center from point P. So, this is the third aspect of shear center. The second aspect. The third aspect is that once we find out this equivalent set of shear forces and the torsional moment, then the total shear force, as I have discussed in the last class, the total shear flow is going to be equal to shear flow due to Sx and Sy plus the shear flow due to Mt. So, these are the basic properties of shear center. Now, let us move on to an example which will help us to understand the concept of shear center with better clarity. So, let us take this example where we have a symmetric C section. We have a symmetric, so this has an uniform thickness T. So, this is a thin walled C section. This is open cross section, of course. So, this is thin walled C section of a beam. Okay, let me draw the dimensions. So, this is B, this is also B, and this is H. Let me draw the x and y axis. Let this be the centroid of the cross section. Now, the question is that find the shear center of the cross section. So, let us find out the shear center. So, let me name these corners as 1, this as 2, this as 3 and this as 4. So, the problem is that we need to find out the shear center of the cross section. Now, let us try to understand that this cross section is symmetric about the x axis. Therefore, the shear center has to lie on x axis. So, since it lies on x axis, the only thing that we need to know is where on the x axis does the shear center lie. So, we can find that out if we assume that the shear center is lying at a distance zeta from the web of the C section. So, let this be shear center. So, we have assumed that, so what we have done is that we have assumed that the shear center lies at a distance zeta from the web. 2, 3, okay, on the left hand side. Okay, let us just make this assumption. You will get the exactly same answer if you just assume zeta to be somewhere here or anywhere on the x axis, or either on the right hand side or on the left hand side. The answer will not change. So, I have just arbitrarily chosen that the shear center is on the left hand side of the web of the cross section. Now, how do I find out this value of zeta? So, let me draw a shear force through this shear center, which let me call as Sy. Now, according to the definition of the shear center, since Sy is passing through the shear center, the torsional moment produced by Sy about any point has to be balanced by the torsional moment produced by the shear flow in the cross section. So, let us understand why if a shear force passes through the shear center, there would be no resultant torsional moment in the plane of the cross section. Now, because of this Sy, we know that there is going to be a shear flow in the cross section, which we can find out how the shear flow will be distributed. We have discussed this in detail in the last lecture. So, let us call this as Qs. Now, why does, if Sy passes through shear center, why there is no torsional moment in the cross section? The reason is that this Sy, the moment produced by this Sy about any point on the plane of the cross section will be balanced out by the moment produced by Qs about that same point, and that way the net resultant torsional moment on the beam cross section is going to be 0. So, we are going to use this definition to find out the value of zeta and thereby locate the shear center of the cross section. So, now I just need to find out. So, the next job is to find out. So, the first thing is to find out Qs due to Sy. Now, how can I find out Qs due to Sy? So, we know that for this particular symmetric cross section, Ixy is going to be 0, Sx is equal to 0. If we substitute all this criteria into the expression that we have, we can say that Qs minus Q0, every other term is going to 0. It can be written as Sy by Ixx into T into y ds. So, this is going to be the thing varies from 0 to s. So, this is going to be the expression for Qs when under this condition, under the condition of symmetricity and under the condition that Sx is equal to 0. So, the next thing that we need to do is to find out Ixx. Let us try to find out Ixx. So, Ixx is going to be 1/12 h cube by 2t. So, this is for the portion 2, 3 plus 2 into bt, twice the area of the top and bottom flange, into h by 2 whole square. So, if we calculate this, we have 1/12 h cube t plus b h square t by 2. So, if we calculate this, simplify this further, it is going to be h cube t 1 plus 6 b by h. So, this is Ixx. Okay. So, once we have found out the expression for Ixx, I can always substitute that and find out the final result or final solution for the problem. Now, let us see how to find out the shear flow. So, shear flow. So, let us first consider the flange 1, 2. Now, for flange 1, 2, so for flange 1, 2, so my S is going to be in this direction. So, let me take this to be positive S. So, therefore, my S varies between B to 0. And I just need to express y in terms of ds. So, y is going to be minus h by 2. Therefore, Q12S minus Q0, which is basically Q1, is going to be minus SYT by Ixx into minus h by 2 ds 0 to s. So, that is going to be SYHT by 2 Ixx into s if I evaluate this integral. Now, what is Q1? Q1 is going to be 0 because it is the outermost point on the beam surface. So, therefore, from this expression I can say Q1 to S therefore is going to be Sy into HT by 2 Ixx into S. Now, from this expression I can get Q2 to be SYHBT by Ixx. Now, let us see what else do we need to calculate. Now, by the definition of shear center, we have to take the moment because of this QS over the entire cross section about any arbitrary point on the beam, and we have to equate it to the moment produced by Sy about the same point. Now, let us say that we choose point 3 and we take moment about point 3. So, if we take moment about point 3, so if we take moment about 3, then the moment because of Sy about 3 is Sy into zeta, okay, in the clockwise direction, and that should be equated by the moment produced by the shear flow. So, the moment produced by the shear flow would be Qs ds into the moment arm. Into the moment arm about 3. Okay. Now, let us see. So, to find out, so if we can find this moment, if we know Qs in terms of Sy, from this expression, this expression will give me zeta. Now, let us see, if we choose point 3, then the moment produced by, so about point 3, okay, the moment produced by Q12, okay, so let me write this as so moment produced by moment due to Q12S is non-zero, but moment due to Q23S is going to be 0, because Q23S is in line with it passes through point 3. So, therefore, the moment due to Q23S is going to be 0. Similarly, the moment due to Q34S is also going to be 0, because Q34 passes through point 3. Therefore, if we find out, therefore, it is enough for this particular case, enough to find Q12S. I do not need to find out any other shear flow Q, that is Q23S and Q34S, to evaluate this equation which we name as equation 1. Therefore, we can say that Sy, so from equation 1 we can say that Sy into zeta therefore is going to be 0 to b q1 to s ds. Now, the moment arm is just h. So, the moment arm is just h. So, therefore, if I write down the expression of, so what is q1 to s? So, q1 to s we have evaluated earlier, and q1 to s is Sy Th by 2Ixx into s. So, if we plug this in here, we will get Sy Th square by 2Ixx into 0 to b s ds, right, because the moment arm of q12 is always h with respect to 3. So, this one there is the moment arm of q12 about 3. So, that is always going to be h. Okay. So, therefore, we final expression that we get is this, and since q12 is between 0 to b, now my limit is going to be from 0 to b. So, I can find this as Sy Th square by 2Ixx s square by 2 and 0 to b. So, this can be therefore written as Sy zeta into Sy Th square by 2Ixx into b square by 2. So, Sy and Sy cancels out. So, therefore, I can write that zeta is going to be b square h square t by 4Ixx, which is into Ixx. Let us, so if we substitute the expressions of Ixx, we are getting this as 4. Ixx is h cube t into 12 by 1 plus 6b by h. Now, we can cancel this out. We can cancel this out, and we will be left with h, and this we can left with 3. So, therefore, this will simplify into 3b square by h plus 6b. So, this is therefore the answer that we are looking for. Therefore, the shear center of the cross section C, so the C cross section is on the x axis because of symmetry, and it is at a distance. So, if this is the shear center, this distance is zeta, which is given as 3b square by h plus 6b. So, this is the answer that we have. So, therefore, it is very simple to find out the shear center if we carefully choose the point about which we are trying to find out the moment. Thank you.